This video is about some special discrete random variables. We know random variables are functions. There are functions with very special properties, so there are also random variables with very special properties. This video discusses about 3 different discrete random variables. They are associated with very special and ubiquitous distributions. They even get their own names. We know to specify the distribution for a discrete random variable, we only need to know the PMF function, which is the probability mass function, right? In the later discussion, this is what we're gonna do with respect to 3 different random variables. We first introduce their background story, what kind of sample space they are working with, what kind of the numbers they're gonna generate. And then we introduce the PMM function associated with each of these random variables, and in the end discuss the properties concerning those random variables. The first one, binomial random variable. This is the background story. We're gonna throw a very special coin n times. And for each flip, we have probability value p to get a head, and 1 minus p to get a tail, or bottom. Let x denotes the number of heads in n throws, and this x is a binomial random variable. The distribution of x is the binomial distribution with parameter n and successful rate p. Or sometimes we say x follows binomial distribution with parameter n and p. We use this notation to denote such statement. So you can pause the video for this moment, I think, if you can derive the PMF function for this random variable. The PMF function of x is essentially given by this formula. Based on the background story, we know x can only take values either 0 or 1 until n with non-zero probability, right? The other values are not possible because we're gonna only throw n times. So at most we have n heads, or if unlucky, we probably have 0 heads. For a specific outcome with with k heads, we know this is the probability for such one outcome, right? P to the power k times 1 minus p to the power n minus k, right? This is the number of getting tails, and we have k heads in total. How many outcomes of such kind? How many outcomes would have k heads out of n throws? We have n choose k such outcomes, and each outcome have this probability. So in total, the probability of event that we are getting k heads out of n throws is equal to this value. Okay. For a special case, if we have n equal to 1, so we're gonna only throw this coin for 1 time. It's also called Bernoulli distribution, because n now is fixed to be 1. It's also have a very special notation for that. It's Bernoulli with successful rate p, right? So if we only throw 1 coin for 1 time, and the coin has rate p to get a head, then the distribution of, so if I let x still denote the number of heads in 1 throw, then the distribution of such x would follow Bernoulli distribution with parameter p. Now let's take a look at some figures of the PMF function. So if we fix n equal to 10, p equal to half, this is the PMF functions look like, right? Indeed, the largest probability mass, while most probability values is assigned, they are assigned to the number 5, right? Because here we have successful rate equal to half. So apparently, if we throw 10 times, the most likely possible of number of heads you get is 5. Okay. Now, if we increase n from 10 to 100, this is what it looks like. Given the graph is of the same size, apparently we are getting results closer and closer to the relatively centered area. And if we include n to much larger and larger cases, it's gonna be even centered to the center area. And apparently, if we consider the average value of xi's, it's getting closer, more likely to getting closer and closer to half, right? Now, if we shift the value p from half to some value, to some smaller value, you can pause the video here and think what would happen to the PMF function. Well, if the successful rate of getting head is getting smaller, apparently more probability is gonna shift it to smaller values, right? Because it's getting harder and harder to have heads, so you're gonna see the probability, more probability masses are shifted to the left part. And in this special case, right, the most likely results is 1. Out of 10 throws, it's more likely to have only 1 head. Okay. And if you consider this 1 over 10, well, it's exactly equal to p in this case. Very interesting connection with the outcomes you have and the successful rate, isn't it? The second random variable we're gonna introduce is called discrete random variable. Here is the background story. Suppose we have a set of numbers, C. C contains n different numbers. And we're gonna throw a n-sided fair die. Each side is marked with a different number in C. We denote x, the number of the outcome you can get by throw this die for 1 time. Apparently, this event, x equal to small x for any small x from the C, right? All those events are equally likely to occur for different x's from C. Then we say the distribution of x, random variable x, is the discrete uniform distribution with the support equal to C. Or we say x follows the distribution, discrete uniform distribution with support set C. Okay. Then what is the PMM function for this distribution, for this random variable? You can pause the video at this moment and think about it. The result is quite simple, right? The PMF function of x is essentially the probability of x equal to x, given they are equally likely, there are n possible outcomes. Each of them are equal likely, so we have this probability value equal to 1 over n. Well, particularly, what is the probability value of this event? X equals to x1 or x2. Those are not identical values, they are different values, and they both belong to C. Well, then it's gonna be 2 over n, right? Of course, here we have n larger or equal to 2, because C already contains 2 different values here, x1 and x2. The discrete uniform distribution actually connected with the binomial distribution we just discussed. A special binomial distribution with n equal to 1 and p equal to half is also a discrete uniform distribution with the support 0, 1. Because the binomial distribution with n equal to 1 and p equal to half is essentially Bernoulli distribution with parameter p equal to half. That is essentially the distribution associated with the random variable of getting 1 if you have a head and 0 otherwise. And given the successful rate is half, 50-50, so it's a discrete uniform distribution of either getting 0 or 1. This is the second special discrete random variable we introduce. And the last one is the most challenging one. It's called, among the three is the most challenging one, I think. It's called hypergeometric distribution. And the distribution for this one, it needs to be specified with 3 different parameters, W, B, and N. For a hypergeometric random variable, this is the background story. Suppose we're gonna mark N different balls with stars from a urn with W white balls and B black balls. And each ball is equally likely to be marked with stars. So we're gonna pick arbitrarily N balls from these W plus B balls and mark these balls with stars. And X is the number of balls being both white and marked with stars. If X generated by this way, we will say X follows hypergeometric distribution with parameter W, B, and N. Okay. So what is the distribution of the PMF function of X then? What is the distribution of X then? You can pause the video at this moment and think for a while. Well, the result is like this. So how many outcomes we can choose? N balls from N plus B balls. That is all the outcomes we have, right? And what if we have K balls marked with stars and they are white balls? So basically it means we need to choose K out of W white balls and the rest need to be chosen from the black balls. So how many choices we have though there? That's gonna be B choose N minus K, that many choices. And K here has to be within this range because, well, it has least need to be larger than 0, which is for sure to be true. And this case is because suppose N is larger than B, right? So this is at least you need to draw N minus B white balls. Of course, because at most we're gonna have N balls, we're gonna mark at most N balls. So K has to be smaller or equal to N. And because X denotes the number of balls being both white and marked with stars, the possible numbers could be taken by X has to be also smaller or equal to W as well. So this is the range of the support of X. Okay. This hypergeometric distribution or this hypergeometric random variable has a very special property. If we have X follows hypergeometric distribution with W, B, N as parameters, and Y follows this distribution with N, W plus B minus N, and W as its parameter as Y's parameter, those two random variables, they have identical distribution. The results follows exactly from this identity. So if you expand them by the definition of binomial coefficient, you're gonna show those values are equal to each other. If you look at the left-hand side, right, that is essentially the probability associated with this event, X equal to K. And if we look at the right-hand side, it's essentially is the probability value of Y equal to K. So indeed, they have these two random variable. If they follow these two hypergeometric distribution, then the distribution, the PMF function for these two random variables are equal to each other for different choices of the K. And because we know PMF function determines the distributions of discrete random variables, essentially they have identical distribution for random variables X and Y. Here's also a simple story proof for why they have this identical distribution. You can pause the video for now and think about if you can figure it out yourself. Okay, the idea is, well, we can consider this as the background story for the Y. So we're gonna mark W different balls with color white from an urn of N balls with stars marked with stars and the rest balls with all stars. And each ball is equally likely to be marked with the color white. Okay? And let's Y denote the number of balls being both white and marked with stars. So think about the background story that we're gonna generate, that X comes from. So essentially is you can consider we first draw the balls, then we mark the balls with stars. For the Y case, you could think we first mark those balls with stars, and then we're gonna draw those balls with different colors. In the end, what we are care for is always the number of balls being both white and marked with stars. And by symmetry, we know XY should follow identical distribution, which is indeed the case. Okay, so here we introduce 3 different discrete random variables, 3 different discrete distributions, and there's more distributions with very special properties. Those perhaps you're gonna encounter in the future. And thanks for watching this video.